before I dive into Python, which is really the main point of this presentation today, I just want to tell you a few things about who I am and the center that I work at. I come from the Yale Center for Research Computing, which you can think of as the supercomputer center at Yale. So we operate all of the sort of supercomputers at Yale. They're called compute clusters. We have tens of thousands of servers. They're all out at West Campus. Our center is about 20 people. We sort of divide between engineers who run the systems and people like me who help users. My job is to do everything that'll basically be of use to users. So anything from helping people one-on-one to giving courses like this, to installing software, to debugging problems, to designing the next systems that we're going to install, et cetera, et cetera. So you can use our services for free. We exist really to help you. So if you find yourself in the need of computing that goes beyond what you can do with your own laptop or your the servers that are in your lab, please feel free to reach out to us, and we'll try to help you. Normally, we're located at 160 St. Ronan, which is, if you know where the Yale Garden is, it's right next to the Yale Garden, kind of where St. Ronan hits Edwards, the back of Science Hill. And we hope to be back there soon. We're sort of starting to go back. And our website is at the bottom of the page there, ycrc.yale.edu. So like I say, feel free. We give lots of different workshops. This is an example of just one. And we would love to hear from you guys. So Python, why am I spending a couple hours talking about Python? Why should you learn Python if you don't already? I am a huge advocate of Python. I've been programming for many, many years, and I guess it was about 15 years ago I started using Python, and I think it's the best language out of the many that I've used and employed to solve problems. And why do I think that? The first is that it's just a really easy language to learn and to make progress in. I think it's got a sort of a design aesthetic that's really strong. It's got an easy learning curve. It's very intuitive. It holds together really well. You're not surprised at the way things work in the way that I find with things like Perl. I'm constantly surprised. It's not to say you can't do good things in Perl and people learn Perl, but boy, it's rough at the beginning with Perl. R is a little bit like that too. I think it's probably a bit easier than Perl, but again, R can really shock the heck out of you when you are first learning it. It's not really doing what you would expect. So that's one thing. I think it's just an easy language to learn. Another aspect of it is that there's just a huge user community with a lot of libraries, a lot of third-party libraries. So there's just a lot of support already built in. You don't necessarily have to build everything yourself. That's of course true for R as well. But it's a big advantage. The third thing is, and this is maybe a little less obvious, that you can write big codes in Python. A lot of Google is written in Python. So it's not just a scripting language for little knockoff, one-off projects, although it's really, really good for that. You can write a simple program in Python faster than you can write it in almost anything else. But you can also write big, serious applications. And you might think that because Python is an interpreted language, that would be a really inefficient thing to do. But it turns out that most of those libraries that are the sort of that implement the more complicated parts of Python are all actually written in C. And so in practice, most of the computing that you're doing is actually being done in C. It's just you're not having to program in C. So Python is combining this sort of ease of use. It's nice for the humans. It's easy to use, easy to understand. There's a lot of support for it. And it can be, while not as efficient as hand-rolled C, pretty close in a lot of cases. And certainly way more efficient for you to program than it would be to write C. So the first thing you'll have to do is install Python. There's a lot of ways to do that. And in fact, a lot of computers these days will come with Python already installed, so you can just go ahead and use it. That said, there's a package called Anaconda that we really like a lot. It's a kind of a packaging of Python. And it's what I like about it. I like several things about it, actually. And we use it really extensively at the center. It's very easy to install, but it comes with a package manager. And so once you have your base Python installed, you can use Anaconda to go ahead and install lots of add-on packages. And not only does it make it easy to do that and allows you to do that without being an administrator, which is very useful. It's just a user level install. It has a pretty good understanding of the dependencies. So if you install application X that happens to have this huge chain of dependencies, by and large, it'll figure that all out and it'll install everything for you. So it kind of keeps track of all that. You don't have to go through all the steps of installing all the different pieces. The third thing it does, which is really powerful, is that it allows you to create custom environments. So like little sandboxes. So for some project you're doing, you can set up an Anaconda environment and install just the packages you need for that project. And then later on, when you're working on some other project, you can start with a clean environment and install packages into that different packages. So why is that good? It's good for a couple of reasons. One is it'll avoid conflicts between those sets of packages so that you have a nice, clean environment that only has what you need for that particular project. The other thing that's good about it is it kind of documents what your environment is. So maybe sort of think about reproducible science, reproducible work. If you just keep piling on more and more and more libraries into your environment over the course of years, it can be really hard to know exactly what your environment is. So if you want somebody else to be able to do exactly what you did, how are you going to reproduce that environment? That's like a common problem with R. Over time, you just keep installing more and more R libraries into one big clump. You're going to start getting conflicts, and you may not know exactly what it is that you have. So Anaconda allows you to manage all that. So what can you do with Python? You can do, so I would argue, to first approximation, you can do pretty much anything you could do with any programming language. And the nice thing is you can do it, you can stay within one language instead of having to use Java for this and Bash for that and C for this other thing. That way you can build up some real expertise in that one language and be able to quickly do the things that you want to do. But some typical things I see all the time are messing around with files, converting them, filtering them, automation. So you might think of doing that in Bash, and you can, but I actually find it easier to program in Python than in Bash. You can do lots of statistics, et cetera, et cetera. So pretty much anything that you would do in most languages, you can do in Python. The sort of key feature about Python, which it shares with R and with Perl, is that it has this kind of dual nature, that you can think of it as a programming language in which you write programs and run them, sort of typically. It's just the kind of thing you do with Java or C. But you can also think of it as an environment, as an interactive environment. So you can just start it up and start typing, and things will happen. So that, in that sense, it's kind of like R. As far as I know, Perl doesn't let you do that, or at least there's no standard way to do that in Perl that I'm aware of. So that's what I'm saying here. You can just run the interpreter interactively, just type Python and then start typing Python stuff in it. Or you can write a program, you can write a file, like myscript.py, and then run it. A third way to do it is to run within a notebook, a so-called Jupyter notebook. And that's what I'm actually doing here. I'm running, and let's see if I can show you this. So this is actually a Jupyter notebook that I'm showing you here, and it has cells, and each cell can either contain text or Python code. And the Python code actually has Python behind it, and I can run the code. We'll see that in a few minutes when I start actually running real code. I'm throwing one more thing on top of here. I could, and I was tempted to just show you this, but it's so hard to read. I didn't want to do that. So I'm actually, I have a presentation layer on top of here. that turns each cell into a slide. But it's basically just showing me a slide. Of course, that didn't work. Okay. You guys, yeah, you are seeing that. I don't know how to get rid of this little bar here. Okay. Okay, I'm going to skip. I have in the presentation, which will be provided after this to you, some instructions on how to install Anaconda, but I don't want to show you any of that here. It'll take too long. One quick note, there are actually two major versions of Python that are available in the world. This has been true for quite a while. The old version is called 2 and the new version is called 3. It should be the case that you really are working only in 3 now. It's just that there's a lot of Python 2 out in the world and you'll run into it. So I just want to point that out, that there are a number of differences between the two. The two that you're likely to run into as beginning Python users are that they changed the way print worked. Print used to be a statement and now it's a function. So you have to put parens around the thing you're printing. And weirdly, in the old days, if you did integer division, it would give you the truncated result. So if you did, I think I have here, yeah, if you did 7 divided by 3 in Python 2, that would be 2, which that led to some pretty weird bugs, actually. So they changed that. This is funny little magic you can do in Jupyter Notebook, where this notebook is actually executing in Python 3, but I can put that little magic in there and it'll execute it in Python 2. So this gave me an error because it's now a function. So that's how things work now. You can see, yeah, you can see that. Okay, so I should say the beginning of this is going to seem pretty basic. I'll try to go really quickly through it for those of you who programmed. If you have programmed this, I think the thing you'll come away with is, wow, this all looks pretty familiar and straightforward. So the basic building blocks, types in Python, you've got integers, floats, strings, and true or false values, Booleans. And you just go ahead and assign them like this. So you see here, I've assigned values to a bunch of variables. And for those of you who programmed in a language like Java or C, the thing that leaps out is I didn't have to declare anything. I didn't have to say, well, radius is an integer and pi is a float. Oh, wait, is it a string? In this sense, again, it works similar to the way R would. You can mix types and Python will kind of figure out what the right thing to do. It'll kind of take the most general type and convert everything to that. And you can reassign to the same variable name values of different types. A little bit more about strings. So the basic way to define a string is with quotes. You can either use single quotes or double quotes. The kind of weird thing about strings is once you create them, you can't modify them. So here I've got S as some string assigned to it. And if I wanted to change the second character in S by doing sort of what you might think you would do, like what you would do in C, I'm going to get an error. It says you can't assign to elements of a string. So a string is immutable, and they do that really for efficiency's sake. There are mutable strings. There are a different class of strings, but the basic string is not mutable. As we'll see in a bit, everything in Python essentially is an object. So there's a lot of object-oriented programming possible in Python. And strings are objects as well, and they have all these methods on them. So I can, one of the methods called split. So if I run split on S using L as the splitter, it'll split my string hello every place where it's on L, consume the L's, and return me the pieces that it split. So just to give you a sense that Everything in Python is an object. The next really important data structure is lists. They're like arrays in other languages. So I can go ahead and assign this series of numbers to the variable numbers, and then I can dereference the third one. You might be surprised that I got a 4 instead of a 3 there. That's because Python starts numbering at 0 instead of 1. That's the same thing C does. Other languages start numbering at 1. So Python and C both consider the first element of something to be the 0th element of it. So that's why we get a 4 there. You can do things like this. So I can get a sort of a piece, a section of a list by giving a start and a stop. So I get the 5th through the 7th element of the list. You might be surprised again that I only got 2 elements out instead of 3. The array slicing like that is, or list slicing in Python is defined as you start at the first number and you go up to, but not including the last number. And that just turns out to be useful in for a bunch of reasons, but you really just need to memorize that. You can also do strides. This is kind of fun. You don't do it a lot. So this is stride by 2. So give me, starting at 1 through 6, give me every other element. I should, yeah, this is a little awkward, but if there are questions, please ask. So here's something that's maybe a little more surprising. I can assign a floating point number into this list, even though all the other elements of the list are integers, and that's totally fine. Python doesn't care what the types of the elements of the list are. It's just going to group them together, and that works just fine. It's a little unusual to have something like this, but I just want you to understand that a Python list needn't all be of the same type.
Does it mean that you can have numbers and strings in the same list?
Lists, I was hearing some feedback there. Lists are more flexible than arrays in the sense that you can expand or contract them. You can nest them. So in many languages, there's something like a linked list, and a Python list is more like that. So here, for example, let me do this in 2 steps here. So I can actually put a list inside of a list. So I've replaced the second element of the list, which used to be 3, with this other list. Okay, so you can get a sense, you can build some kind of complicated data structures this way out of nesting lists. This is, take it from me, you can do a lot of complicated things with lists. We won't get too deep into that. Okay, so the next one after lists is tuples, and they're almost exactly the same as a list. They're ordered. You can put things of different types into the tuple. The difference is these are not modifiable. So once you create a tuple, it can't be changed. So here I've created a tuple, but I can't write into it. So I get a kind of similar error to what I got when I tried to do that same thing to a string. So they're immutable the same way a string is. Otherwise, they're very similar. The way you do subscripting is the same. They also start counting at 0. And you might think, well, what's the point of that? Why wouldn't I just use a list? You'll run into tuples a lot being given to you from some function you call in Python, and that's kind of a clue. The reasons tuple exists is they're extremely efficient. So that flexibility that lists have comes at a cost. It needs to be able to at any point modify that list in a whole number of different ways. Whereas a tuple, once that tuple is created, it's set in stone, and the system can take advantage of that. So the reason I mention them is you're going to run into them pretty frequently as return values from functions that you call in Python. You may not generate them yourself too often, but you'll run into them. The next and maybe most interesting data structure is dictionaries. And this is what Python calls, what kind of everybody else calls hash tables. So if you've seen hash tables in other languages, that's what this is, a dictionary. And the basic idea with a hash table or a dictionary is, rather than thinking about data arranged in order where you ask for the 5th element or the 10th element, you give the values names. And when you want to get that, that value out, you give the name and you get the value back. So for those of you familiar with using hash tables, this will all seem very straightforward. But here's the syntax that Python uses. Use these curly brackets. And you can see here I've created a dictionary with 4 elements. It has integers as the values and strings as the names, as they're called keys actually in Python. So the keys are penny, nickel, dime, quarter, and so forth. So now I can retrieve the value that is associated with the name dime by doing that. So pretty straightforward. What's important about dictionaries, and in fact, the reason hash tables in general exist, is when they're implemented properly, they're incredibly efficient. Looking up something in a dictionary should be a very small constant time, no matter how big the dictionary is. And hopefully at the sort of the end today, we'll see an example of that. Once a dictionary is created, you can continue to add to it. Let's go off the screen there a little bit. Let's see if we can get that. So I can create a new element called $half that assigns to the value 50. Okay, so those are some very basic data structures. You can do a lot with just those data structures. Now I want to just quickly turn to some control flow statements. So how we take the stuff we've learned so far and turn it into a program, into control flow. And again, this stuff is common among all programming languages, so it'll look very familiar. The syntax will just be a little bit different. So the first one is if, just a conditional. You can have an else as well. So here is actually the first legitimate snippet of Python code we've seen. It's, what is it, 10 lines. So I'll go through it line by line. So the first line, import random. This is the way that Python allows you to use packages, to use other sets of code. So there's a package called random, and it has a bunch of useful functions in it, including a function called randint that lets you generate a random integer. So we're going to generate a random integer between 0 and 100, and then we're going to test that number. If it's below 50, we're going to do this block of code here. Oops, this block of code. This isn't working, but you know what I mean. Oh dear. And if did I break it? Yes. Well, I'm not going to talk about this one then, so I won't run it. I'll talk about it. If the number is greater than 50, we'll do this here. Furthermore, here we've got an interior if that is going to, if the number is even smaller, if it's less than 5. Bet I can fix this quickly. Wow, that's really messed up. I'm not going to bother. Okay. Moving on. While statement is similar. Here, we're basically going to have a loop and with a test. And so as you can see here, again, we're going to generate random numbers, and we're going to start summing them up. And when that sum exceeds 100, the while will turn false, and we'll break out of this loop and print done with loop. So this, we'll go ahead and run this one. So you can see it ran a whole bunch of times and eventually got to.
I have a quick question.
Okay.
Do you always have to refer to the package name prior to the function call? Or is there a way to not
No,
have
there's
to do that?
another. So the question is it always necessary to use the package name before you do the function call? As I did here, I said random.randint. There's a different way to do the import. This is really messed up here. I wonder. Shoot. You say import randint from random. So it's just a different syntax. But if you do that, then you can just use the function name randint without qualifying it. So there's different ways to do the imports, and depending on which way you do the import, that will affect how you refer to the individual function. Seems like my notebook and Zoom are not playing nicely together, but we'll see what we can do here. Okay. Was while reasonably clear? So again, the idea here is you're defining a loop, and the loop has a test, and every time through the loop, you first run the test. If the test is true, you do the body of the loop. If the test is false, you break out of the loop and continue on below it. So if we could see the bottom of the slide, we would see the print done with loop. So another kind of loop is a for loop. And again, you've seen for loops in pretty much any language that you've used. However, this is where Python is just a little bit different. So the typical for loop that you would see in C or Fortran, for example, or even Java, loops across integers. So that, which is, very reasonable thing to do, but a little bit constraining. So that would correspond to this Python, where we just loop across the numbers from 0 to 3. So every in the body of the loop, we have this print statement, and we'll print out the current value. So this would correspond to a very simple for loop in C, for example. There's a very nice function in Python called range that will give you all the numbers up to, but not including, because that's what Python likes to do, the number that you give it as a parameter. So this will give us all the numbers from 0 to 9. Oh, how do I get that down there? It's very frustrating. If I go out of full screen. Yeah, maybe I'll just try that. So to show you that for loops in Python are much more flexible and much more powerful, I can do for letter in this string, and what it does is it loops on every letter in the string. Okay. So what's going on here? For loops in Python are really general. They take after the in something that's iterable. And that can be a whole lot of different things. It's something that Python can query and say, give me your next value. So you can write your own objects that know how to provide values one at a time, or strings know how to provide one at a time. And what would happen up here is lists know how to give one at a time. So it's not so much that we're iterating over integers here. What we're doing is iterating over a list, where a list knows how to generate one value at a time. And lots of objects in Python know how to do that. And you can use any of them to do a for loop. And so that's what's going on here. And we'll see in one of the more complicated examples of one of these kind of iterations. And actually, in a minute, I'm going to show you how to do that with dictionaries. So, so you can use a for loop over a dictionary. And I don't know, what might you guess we would get out here? What is the value that's going to be produced by coins on each iteration? It's kind of two possibilities, I guess. It could be either the key or the value. And it turns out they chose the key. So when we iterate over a dictionary, what we get are the keys. Of course, we could just very easily say coins val here. And then we would get the values. The other thing we can do is there's a method on dictionaries called items. So coins.items is an iterator. It knows how to produce one value at a time. It turns out the value it produces each time is a tuple of the key and the value. So if we do that, we get 5 iterations. Each iteration returns a tuple. Remember, I told you that tuples get used internally by Python. This is an example of that, where each iteration through this for loop generates a tuple, and that tuple contains the key and the value as a pair. So that's kind of nice. But it gives you a sense of how general the for loop can be in Python. So the next, this one's kind of important. So when you're doing a loop, either a while loop or a for loop, you needn't go to the bitter end until the test turns false or until you run out of values. You can do some things on the way. One thing you can do is continue. This basically ends the current iteration, pops you up to the top, and lets you continue with the next iteration. So what this code is going to do is anytime, so that the % is mod, so it's basically testing for whether the number is odd. If I mod 2 isn't equal to 0, then the number is odd. So any odd numbers will cause us to execute continue and jump back up to the top of the for loop. Other numbers, even numbers, won't do that, and we'll go ahead and print them. So the end effect of this completely nonsensical bit of code should be to print all the even numbers, which is what happened. Another thing you can do in a loop is break it. That means just stop the loop altogether and continue below the loop. So here, we're generating all the numbers between 0 and 10. As soon as we hit something bigger than 5, we break and we'll stop printing. So we should basically see all the numbers up to 5, which we do. So there's just 2 things you can do in loops. Now these little code snippets that I've been showing you that maybe you thought about, or maybe it just looked so natural you didn't think about it. How did we know where the code blocks begin and end? In things in C, you use curly brackets. In Fortran, you use begin end. If I remember right, Java uses curly brackets. It's been a long time. You don't see any of that stuff in Python. And the interesting thing is, your eye kind of does it for you because of the indentation. Like you didn't really miss. Let's go back, maybe here. This one. So how did you know that last print wasn't a part of the loop, but the print count was part of the loop? Well, it's indented, right? So kind of naturally. Well, it turns out that's exactly right. And that's kind of maybe the most surprising thing about Python. And there are people who don't like that about it. It seems very strange that it's indentation that defines blocks. But that's what's done. So it's white space that defines the blocks. If code is indented to the same level, it's in the same block. You don't have to be incredibly consistent with that, but if you want your code to be readable, you should be very consistent. So the kind of standard is 4 spaces in for each level of block. And if you write your code that way, it'll be much easier to read. And a lot of editors will actually do that for you. If it hits tab, it'll move you over by that amount. So yeah, so indentation is actually semantically meaningful in Python, which is very unusual. A couple more fun things that I can show you. One is something called a list comprehension. I like this because it's very Pythonic, as they like to say, the adjective for doing cool things in Python is it's very Pythonic. Let's say you had a list of numbers and you wanted to multiply each of those numbers by 5 and create a new list. Well, this is the sort of the manual way to do it. You iterate through the list of numbers and you multiply each number by 5 and you append it to a new list. This is one way to do that. So you end up, sorry, I have to say new numbers here for this to make any sense at all. Multiplied by 5, right? That's what I said. But there's a different way to do it, with what's called a list comprehension. That's what this line is here. So the way list comprehension works is you use the brackets, the normal list sort of generation brackets, and inside there you have what looks like a for loop. So you do for something over something. So this part is a standard for loop in Python, and it's assigning something to number for each iteration. And then over here you have an expression that presumably, it wouldn't have to, but presumably uses that variable. And so this code runs through all your, iterates through all the numbers and does the expression times 5 on it, returns a new list. So a list comprehension always returns a new list, which we've then assigned to new numbers. So it works the same way, but it's more concise. Functions. You've seen functions in other programming languages. There are lots of functions in Python. They're pretty straightforward. Use the keyword def. So this defines a function. We're going to define the world's simplest function called area, which multiplies width times height and returns the value. So when you execute the def statement, it actually defines the function, assigns it to a variable essentially, and then we can go ahead and use it. So of course we can put different values in here and get different results. So pretty straightforward. So summarizing, I've shown you some very basic types. I've shown you some more complicated types, and then some very basic, so we call control constructs, things that allow you to glue statements into more complicated programs. And you'd be surprised what you can do with just that. So it's very basic stuff, but a lot can be done with only the stuff that I've shown you so far. That said, probably the next thing you'd want to know is, well, how do I print something? And I've been doing some of that already in the notebook. And but I want to show you a little bit more specifically how that works. So it turns out, so the basic thing, you say print, and inside parentheses, you put what you want to print. So that's very straightforward. Of course, there are ways to print the files and send it to the screen. You'll see that a bit later. What if you want to combine constant strings and variables? So like here, I want to print simple stuff and the value of I. Well, one way to do that is, and this is kind of a very old-fashioned way, is I call this the function str, which turns anything into a string. So I'm going to turn this integer into a string. And then I'm going to do string concatenation, which is what those pluses do. So I'm concatenating 3 strings, simple stuff, and whatever the value of I is, which in this case is 5, and then printing it. So that's a very simple way to sort of format a bunch of stuff into a printed output. But you'll find that it gets pretty irritating pretty quickly once you have some complicated stuff that you're trying to format. So here are some more complicated ways to do things. The old school way, this first line here, that is almost exactly C, and is admittedly really gross. But if you're used to printing in C, that will feel very familiar and not a big deal. But I don't really recommend it. For a while, the improved version was this thing in the middle using format, which I don't like, and I never really used it enough to get used to it. I did a lot of C, and so the C way didn't seem that bad. And then recently, starting with Python version 3.6, they have this really cool thing called F strings, which is probably what you should do. And there's no reason to use anything under 3.6 anyway. What it does, so the syntax is maybe a little squirrely. You put an F before your string, and then anything that's in braces that's inside the string will be considered an expression to evaluate. So it will evaluate that expression, it will convert it into a string by default, and print it out. So it'll sort of stick it in there. So basically what's happening here is it's going to plug the current value of X in here. So this is showing you can actually do some real stuff in your expression. You can call math square root on X. And so this will give you the square root of X. And then optionally, after a colon, you can put a format string. So these format strings allow you to say what the type of the thing is, how you want it to be expressed, and how many significant digits you want, stuff like that. So there's a bunch of sort of formatting options you can apply optionally like that. So if I run that code, you can see that they all work, and it's basically different ways to do the same thing. But the F string, I think, is really nicely concise and easy to understand. So I'm a big fan of that. I've mentioned already a couple times that everything in Python is an object. You'll find as you grow as a Python programmer that you're going to make more and more use of that. Those objects have lots of different methods that you can use. You can create your own objects, so you can define your own class types and stamp out objects from them. So all the normal stuff that you're used to in other languages, other object-oriented languages, is available here too. And there's this nice function dir that you call dir on some object, and it'll tell you all the methods that it has. So for example, here I've created a list, assigned it to the variable numbers. One of the methods on lists is clear, which empties the list. So I end up with an empty list. But there's lists and strings have very large numbers of functions that do all kinds of cool things. So that you don't have to write all that yourself. You can just use the method on the object. Strings, like I say, have a bunch. So you can partition a string. So partition basically brings a string in two, and you can split a string, which they work similarly as splitting a string actually consumes the thing you're splitting by. And just to show you this dir function in real life. So S is a string. So look at all these methods that strings have. We've seen a couple. Split is in here, but there's things like find and replace and convert to uppercase, convert to lowercase, all kinds of stuff. So all that's built in. Okay. So that was intended to be a whirlwind tour through very, very basic Python. And the next thing I want to show you is a series of examples of using Python to solve particular problems. But maybe any burning questions on that sort of intro material first? Yeah, one question in the audience. Yeah, will you have access to the slides? Yes. There are two ways you can have access to slides. One is there's a URL that you can go to where you can actually get a live version of this notebook in the cloud, actually. And let me be brave and go back. How hard will that be? Let me see. I think if I there, okay. Here is the URL. Can you read that? Is that this tiny URL? Is that I can read it? So it's let's see, bigger. So https://tinyurl.com. the fonts here are messed up. So it's Y9166Y1Y. So both of those things that could be L's or could be Y, could be ones are both ones. And so if you go there, what's going to happen is there's this really cool project called Binder that will fire up a Jupyter notebook on a cloud instance for you and let you actually run it. And I'm not sure it'll work with a large number of people simultaneously. We've seen it break because it's free and it's just being hosted by nice people. But you can give it a try. So that's one thing. And if it doesn't work now, it'll work after the presentation. But I'm also going to make sure that you can get a PDF of what I've got here. Okay. Yep.
Hi, I wonder if the order in which you define the function matters. Can we define the function? So in the example, you define the function first, then use it. Can you define the function at the end of the file?
So the question is, do you have to define the function first in the file before you use it? Essentially, yes. The way to think about that is at the point in time when you call the function, it must be defined. So if all of your code is in one file and you're running through that file from top to bottom, that's the way that the interpreter is going to execute it, then yes, you should have your definition ahead of it. Of course, once you split things into lots of different files, then things are a little bit different. And then you just need to make sure that you execute the definition before you try to actually use the function. All right. Yep.
Oh, hi. So I wonder if there's a help function that in like Python, just like what you can find in Matlab, like you can get the function list, and then you can also see how to use each function.
No, so is there built-in documentation for different functions in Python the way there is, say, in MATLAB or in R for that matter? Yeah. Not directly, but some Python tools, some of the debuggers and such have that as a built-in thing. I tend to use Google, to be honest. Yeah.
Okay, I see. Thank you.
All right, let's see if I can clear the screen up just enough that I'm not wasting all my space. Okay. And yeah, I think I'm going to go with that, because if I go full screen, I'm losing all control of the cells. Okay, so I'm going to go through a series of, depending on how much time we have, 3 or 4 examples of actual reasonable problems that are solved using Python. Give you a sense of what you can do, and shows you some of the basic techniques that are very useful. So the first is a file reformatter. And while this seems really boring in many ways, it's something that comes up all the time for me and for people that I work with. If you have these very large data files, especially ASCII files, where you want to do something to the file, and it's not something that's so straightforward that you can just use some kind of smart editor like Emacs or something. Like, you've got to actually parse each line, figure out what's there, and then modify it somehow. Maybe filter it, maybe throw some of the lines out, maybe change some of the lines. And that's, if it's 10 lines, what's the big deal? But in bioinformatics, it's really common to have files that are hundreds of thousands of lines long, and maybe they're not perfectly formatted, and et cetera, et cetera. So being able to quickly bang out a script that will allow you to do that can save you a lot of time. So that's what's going on here. So somebody gives me this file and they say, the 5th column is a little bit messed up. I need to trim 3 letters off the 5th column. So that's kind of what I'm showing here. I want to start with the upper snippet there and end up with the lower snippet. And because you can't really see in this part of the example, but I can't just like literally take a certain character out because as I go further down the file, I see that some of these fields get larger. So the alignment changes, et cetera, et cetera. So, so what we want to do is we want to read in this file, make that change, and write out a new file. It's kind of a dumb example, but it shows you a lot of very useful techniques that are useful in more interesting examples, like how do you read a file? How do you go through line by line? How can you do very simple parsing on each line, on each sort of string that you've gotten out of the file? How do you write out a new file? And then how do you put all that together into a script and run it? So very basic stuff, but kind of a first real Python program. So thinking about it first, let's forget about Python for a second and just think about it in kind of abstract pseudocode. What would this process look like? So we want to open the input file. We want to read the first line, and that one we're not going to change. So, you know, this header line here, this thing, we don't want to change that. So that's another reason, you know, you've got to be a little bit careful how you do this. You don't want to mess up that line. Then we want to go through the second and all subsequent lines of the file and process each one. And that's going to look like reading it in, finding the fifth column, modifying it, putting it back together, and printing out the whole line. Just do that for every line. So for this first example, I'm going to really do this absolutely step by step. So what does step one look like? Opening the input file. The function to open a file is open, and you give it a file name, and it returns something called a file pointer. It's a Python object. You don't typically look inside that object, but it's a very important object. And it's what you then use to read from the file. So this, it returned you a file pointer, and we assigned it to some variable that we happen to call file pointer. I actually tend to call it FP. That's kind of a standard shorthand. So had I written this line of code, I would say FP equals open bad file.txt. So I can go ahead and execute that code. And you can actually ask Python to print out file pointer. That's another interesting thing about the object orientation of Python. Every object can have a kind of print me method, and you can customize that to do whatever you think is reasonable. So what the folks who implemented file pointers chose to do was print out some stuff about the open file. When you print file pointer, this is what you get. And basically says it's been opened for read mode, and here's the encoding, and here's the original file name. So once you've got that file pointer, you can use that to start reading from the file. So that's what we see here. So I'm repeating the open. So we're just building this program step by step. And then I'm going to call read line on file pointer. And that's going to return me the next line in the file. So read line always returns the next line. Internally, file pointer's got a pointer, and it knows where it currently is in the file. And read line will advance you by one whole line and return what it found. Somewhat oddly, it returns also the line ending. I don't know if you know this, but in an ASCII file, there's a kind of invisible character at the end that tells the system that this is where the line ends, and that's usually hidden from you. In Python, when you read line, it returns you the entire line, including that line ending. And so if I just do this, and if I do it right, I actually have two line endings there, which you can't actually see because it's at the end. But if I say print here, there's an extra space between the header and the here. And that's because we actually ended up with two line endings. We ended up with a line ending that we ingested from the file, and then print added another one. And so you're going to see very commonly the method rstrip called on whatever you get from readline. And what that does is it strips off white space off the end of the line, which in this case has the effect of cleaning it up. And then you just get the single end of line that print gives you anyway. So I apologize for that. That's a little gross. You kind of get used to it. But it's very typical in this kind of code to see people stripping off that extra line feed. Okay, it's just a detail. Okay, so that's how we're going to handle the header line. And now we want to read all the other lines in the file. And so that looks like this for loop. And here's an example of how interesting a for loop can be in Python. What we're looping over here is lines that are given to us from the file pointer. So that for line in file pointer is iterating through the file. It's going to set the variable line to the line next found in the file for each iteration. So for right now, I'm just going to read each line, strip it, and print it. So we can see what we have. I should have mentioned the entire file here is only 5 lines, just so that it's easy to work with. Of course, in real life, we'd have a much larger file. So we can see now that we're able to read through the file and see each line and print it out. So we're sort of at the beginning here. We've got our sort of starting point. I should say also, you notice that this for loop doesn't see the header line. And that's because this first read line up here advanced our pointer past the first line. So when we get to the for loop, we're already at line 2, and we only see line 2, 3, 4, 5. Okay. So now we have the tricky bit of how are we going to parse that each line and find the value that's in field 5, in the column 5, and do something to it. So I'm actually accomplishing kind of a lot in this one line right here. So actually these 2 lines. So for each iteration through our file, we're getting the line and assigning it to the variable line. So line right now is holding the current line. And we're going to do the strip. Strip is just like rstrip, except it strips both ends, which in this case, it has the same effect. The only white space we have is on the right side. So rstrip and strip don't differ in this case. So that's going to return us a cleaned up version of our entire line. And that's a string. And on that string, we're going to call split. And split takes as an argument the thing you want to split with or by. What's the chisel you're going to use to split this line apart? Well, this is a comma separated file. So we're going to split by commas. So the result of fields is that we're going to have a list of each of the elements of that line. Each is a string. So we're going to have a multi-string list. That's what this line does. What this line does is goes in and plucks out fields 4. It's 4 because remember we're starting to count at 0. So the place where that field that we're trying to changes from Python's point of view is the 4th element. So fields 4 will give us what we want. And then we're going to do that kind of string trimming, slicing that I showed you early on. So we're going to get, and this is a very strange string slice. It's saying, give me everything from the very beginning up to 3 from the end. Okay. Remember this, the way the slicing works is you use a colon and you say start, finish. And you can use a minus sign. That means count back from the end instead of counting forward from the start. So the end effect of fields 4 and this slice, I don't know how to pronounce that, is to give us exactly what we want, to give us a modified version of that field that's been trimmed by 3. And we're going to go ahead and overwrite fields 4 in our list with that new value. So we're almost there, and I'll show you what that looks like. So right now, fields is a list. It's a list of strings. And the way lists get printed in Python is, not too surprisingly, is with these brackets and commas. So you can see, and you can see here that we've trimmed this value here that we're interested in has been trimmed appropriately. So it's exactly what we want. But it's still a list. This looks really ugly. So now what we need to do is take this list and turn it back into a nice clean string that's separated by commas. So let me just show you this. So what we've done here is kind of the opposite of of split. We do a join. So we're gonna, using commas, we're gonna join the fields together into a single string and print them out. So if we do that, it gets all nicely cleaned up, and you can see that we have exactly what we want here. Now, just wanted to back up a little bit here. And this splitting and joining is really useful for very, very basic parsing. And you obviously can't do really complicated parsing with it. But for basic, very basic parsing of nicely constructed files, it's very easy. So the basic idea here is split takes as a value the thing you want to split by. So it's going to find every place where there's a comma and chop the string there and consume that comma. So the result of that is is a list that looks like this is a string. And don't be fooled by the fact that we have these commas here. Those commas come from the way lists are printed, and they have nothing to do with the original commas. It's a little confusing. And join works in the opposite direction. So join takes something that you're going to do the gluing together with, in this case, colons. And so then it glues those elements of the list together with that sort of glue, if you will. So like I say, you'll find that you can accomplish a lot of simple parsing using this kind of technique. Now, again, just sort of remind you, everything I've shown you up till now has been in the context of this Jupyter notebook, which is a really nice way to show people things. But and it's a nice way to also experiment. But for production use of something, it's not generally the way you do it. When you're really running something in production, you're probably going to turn your code into a file and then actually execute it using Python. So I want to show you how to do that here. So I'm here in a terminal window on my Mac, and so here is almost exactly the same code as what I just showed you. The difference is this funny bit here, which is both very strange and very important. And if you've done any C programming, that's going to look really familiar. This is really just a kind of an ugly holdover from C. So you noticed when I did it in the Jupyter notebook, I hard-coded the name of the file I was fixing to be badfile.txt. And that's, a terrible thing to do, because who knows what the name of the file is that you're going to fix is going to be. So you want to be able to specify the name of the file that you want to fix on the command line. You want that to be kind of a variable, right? Something you specify. And this is the way you define command line parameters in Python. So you'll see this all the time. I'll explain that in a minute when I actually run it, but that's what that is. The rest of this code is exactly the same. So let me show you how to execute that code. So I've got bad file here. That's the same file. And if I say Python, the name of my script, and I give it the name of the bad file, it goes ahead and fixes it. And currently it's set up to print it right to the screen. So it's just directly outputting it, which I could do this. If you know Linux, I could, sorry, that text. So that would actually capture the output into good file. But let's think of it a minute. What was the deal with that command line parameter stuff, that sys argv1? Well, when I ran my code, my command line was Python name of script and then some parameters. And the way your script sees those parameters is the sysargv. So sysargv is a list that Python is constructing for you and passing to you, and you can then query it. And the 0th element of argv is the name of your script, so it would have been ex1.py. The next one is the first parameter, then the next parameter, and so forth. So sysargv1 is kind of the first parameter on my command line after the name of my script. So that's just a string. I can go ahead and use it any way I want to. In this case, what I wanted to do was use it for my open command. So this is like the most basic command line parsing you could imagine. There's some really nice packages in Python that let you do much more complicated things. So if you have like a lot of parameters with flags or with values, there's a very nice package, for example, called argparse that lets you build very easily and quickly build complicated argument parsing. But for basic stuff, most people use this argv. So that's what that's all about. So, so that's how you would actually turn this snippet of code into a file and go ahead and run it in a sort of more traditional way by saying Python name a file. Okay. So that's it for that first example. Are there any questions about that one? Okay. Yeah, maybe you have a question. Okay. I can't see that on mine. Yep.
Oh yeah, so my question is, I was a little confused by the having to include the print file pointer dot readline to like iterate the readline function by 1 so that you started on the second line. And so I guess I was wondering how you would generally, it's like if you wanted to start on the 3rd line or the 4th line, how you would do that. And if you have to be careful about like, if you're working like in a Python script, like calling that readline function and knowing where you're what line you're currently set to start on.
Right. Okay. So the question is roughly this readline function. How do you keep track of where you are? The person asking the question was a little confused about how that worked with skipping the header line and then moving on. So let me see if I can explain that a little better. Get the code here. So think of it this way. A file pointer always knows, in this particular case, it knows exactly what character of the file it's currently positioned at. So, so when you first open the file, it's positioned at character 0. And any sort of normal read using that file pointer is going to start from that current position, wherever that pointer is. Readline, so there are different ways to use that file pointer. You can read character by character, or you can read line by line. Those are kind of the 2 most obvious ways to do it. When you do the read line, it kind of does several things. So the first thing it does is it takes a look and it finds the next end of line, and it moves the file pointer all the way to just past that. So it sort of positions your pointer to the beginning of the next line, and then it takes everything it found in between and returns it to you as the line that you just read. So now, by doing that read line call, you've both gotten the current line to work with, it returns it, but it's also advanced the file pointer to exactly the character at the beginning of the next line. So, so that's why this works the way it does. So after we do that first read line, now our pointer is positioned right at the beginning of line 2. And then essentially, it's implicit here, but that for loop on the file pointer is actually doing a read line itself. That's what file pointer is using as its iteration mechanism in the for loop. So you could have basically just written a whole bunch of read lines in a script and done them one after another, but the for loop is it's better, because it doesn't care how many lines there are in the file. So really the way to think about it is that file pointer really is a pointer into the file. It's pointing at a particular character, and these methods on it, move it around and do things with it. There's another function on a file pointer called seek that allows you to just push the file pointer to wherever you want. And a really common thing to do is you want to reset to the beginning of the file. So you do a seek to 0, and it would put the file pointer all the way back to the beginning. But you can seek to arbitrary locations in a file as well. So hopefully that answers the question. Any other questions on that first one? Okay. All right, so get back up here. The second example is basically what I call a directory walk. So this is kind of very different. This is like a kind of a utility operation that you're going to do on a bunch of files. So imagine that you had this huge tree of files, thousands and thousands of files across lots and lots of directories. And there were these files in there that had the extension FASTQ, which is a common DNA sequence file format. And they tend to be really big, and so people like to compress them to try to save space. So that's the idea here. We're gonna wander through this huge directory structure, maybe millions of files, and find all of the files that have the ending FASTQ and compress them to save space. And delete the original. Not something you want to do at home. Do it very carefully, but it's a good example. What I like about this example is it shows you 3 kind of completely different things that are very useful in a lot of cases. One thing it shows how to do is how to traverse a directory tree, how to wander through some big collection of directories and files and visit each place. So that can be useful for a whole lot of reasons. The next thing is, how do you actually execute a program from within Python? So we're kind of, it's not really true. We could actually do the compression purely within Python, but I'm going to pretend that we need to call this external program to actually compress the file, sorry. And that is something that you come, if you're building pipelines in Python, for example, you're going to want to invoke programs from within Python. So that's a very useful thing to know how to do. And then finally, how do you know what happened when you did that program execution? How do you test for whether it was successful or not? Okay, so again, looking at pseudocode, what are we going to do here? We're going to loop over all the directories in our huge tree of directories. So I'm pretending I can do that as a for loop. For each of those directories, I'm going to get a list of all the files. For each file that I've found, I'm going to test it to see if it's a FASTQ file. And if it is, I'm going to generate the name of the new compressed file. So it's basically a fastq.gz file. And then I'm going to construct the command that I want to use to do the compression. I'm going to actually run that command, and I'm going to test the results of that command. And just for your understanding, the command I'm going to use is this gzip command. So gzip-c takes an input file, streams compressed stuff out. I'm going to capture it in an output file. Again, there are plenty of good Python libraries to do compression. I don't have to execute an external program, but sometimes you do, and so it's good to know how. So the first thing we need to learn how to do is this directory traversal. And that sounds really easy, and you could write code, your own code to do it, but you would find that there's some subtleties there. it turns out it's really handy that Python has a package that already knows how to do that. So inside of the OS library, there's a function called walk. It's an iterator. The iterators come up all the time in Python. So you give walk a starting directory, and it's just going to iterate through. It's going to dive down that directory tree. It's going to visit every single directory below its starting point and give you a chance to do something. So for example, and this is what I have on my computer here, this very simple directory tree. That's a top level directory called ex2dir, and then underneath that is D1, underneath D1 is D2, and inside each of those D1 and D2 directories, we have one FASTQ file. So very simple. So this is what a for loop would look like that uses OS walk. And this is a really interesting for loop. So let me execute it first, and then I'll talk about it a little bit. So you see it iterated 3 times. So it iterated once for each of the directories. And what I'm asking it to do here is print the current path, all the directories it found in its current place, and all the files it found in its current place. So how does it actually do that? Well, I said OS walk is an iterator. What it returns on each iteration is a tuple. It's a 3-element tuple. The first element is the current path it's gotten to, so it's sort of where it is right now. How deep is it in the tree, and what's the path up to where it started? So it's kind of it's where it is. It's the directory it's currently working in. The second one is a list of all the directories that are immediately found there. And the third is a list of all the files that are found there. I see a question. Question? Okay. So when the first iteration, it's in x2dir. So it prints x2dir here. In that directory is found no file and one directory. So one directory named D1 and no files. And then it descends down one directory into D1. And this time when we print path, we have x2dir D1. And you can see in there, there's both a directory, D2, and a file, F1, FASTQ, and so forth. So it's doing what we want. And of course, if we had a real directory tree here with millions and millions of directories and files, it would traverse through all of those things. Okay, so that's really useful. And sort of step 1 of what we need. So the other kind of completely different thing we need is a way to call a program from within Python. How do we run gzip from Python? And there's another library called subprocess, which is basically the way to do that. So it's a way to invoke a command from inside of Python. Subprocess has a huge number of variations on this. Call is kind of the very simplest and arguably kind of the one you use in the beginning. But trust me, there's lots of variations on this theme, and you can do really complicated, interesting things with some of the other methods in subprocess. But call is pretty straightforward. You give it a command and it runs it. And this shell equals true. This is a parameter to call, and you kind of have a choice. You can either give subprocess call a very basic command and it'll just run it. Or you can say, I would like you to execute this as if you were inside the shell, inside a bash shell or a Bourne shell. And often, if you're used to running things by hand, that's what you're going to want to do. And in this case, we want to do that because I was using this redirection, this greater than sign, which is redirection, to redirect into a file, and that's a shell thing. So I have to say shell equals true in order for subprocess call to work properly in this case. Otherwise, it wouldn't know what to do with that. So I'm sort of saying I have this command and I want you to run it just like as if I ran it by hand in a shell. So this is what that looks like then. And I can actually go ahead and run that code, and it ran, and it returned as 0. So that is essentially a Linux thing. That's the way I think about it. So in Linux, when you execute code, and the Mac is essentially a Unix operating system, it'll return an integer status code. And the convention is, and this is a pretty strong convention, that 0 means everything is good, and anything other than 0 is bad. And so in this kind of situation where you're calling a program, what you want to see coming out is a 0. Some programs will, if something goes bad, the idea is that they'll give you a number, some specific number gives you some kind of clue as to what went bad. So if the error was like this, you'll get this number, like that, some other number. There isn't, that's kind of a program specific thing. There isn't really a general rule for that. But there's a general rule that 0 is good. So essentially what you want to do is check for 0. One caveat there, this is where Linux and Python kind of collide a little bit. A 0 in Python means false. So I don't think I actually mentioned this, but Python will interpret lots of different values as either true or false for things like if statements or while loops. Anytime you're doing a test, a Boolean test, it doesn't have to be true or false. It can be other values. So for example, an empty list is false, but a list with any values in it is considered true, just to give you an example. So you wouldn't want to say if subroutine call, then success, because a subroutine call, subprocess call, sorry, that returns 0, that's actually a value that to Python means false. So just a sort of a strange gotcha there. So you should explicitly test for does it equal 0, and that should be true. Hopefully that makes sense. Okay, so I'm not going to go in sort of very basic step by step on this one. I've got all the code here, but I'm just going to walk you through each line. So at the top here, we have some imports of libraries that we're going to use. So we're going to use OS for the walk. We're going to use sys for the argv for the input arguments, and we're going to use subprocess to execute our external program. So we know we're going to need those. Then you see the kind of stuff I was talking about before with this argv. So in Jupyter, I'm faking the argv. I'm sort of constructing it myself. Python would do that for me if I was running this on the command line. So this code is going to take one parameter, and it's going to be the starting directory, the directory that sort of where we're going to start this tree walk from, the name of that directory. So in this case, it's x2dir. So I'm setting that to the start variable, and then I'm going to do my my OS walk for loop. So you can see that that's the same for loop I showed you before. So each iteration through that loop is going to give me a tuple that is where I currently am, my immediate subdirs, my immediate files. Then I do a for loop over the files. So for file in files gives me one by one each of the files found in that one directory. And then I'm going to do a test. So this test here ends with is a string method. So it returns true if the string has at its end the thing I've specified here, fastq. So file ends with fastq will return true if that string ends with that. So that's my test. Is this a file I'm interested in? So I'm going to skip the next couple for a minute here and just come to command. So now what I'm going to do is I'm going to construct my gzip command, and I'm using that f string here that I mentioned way back. So that's kind of nice. That you can see it's going to plug in the old file name and the new file name and give me back a string that I'm assigning to the variable command. Then just for my own fun, I'm going to print that. I'm going to print running and the name of the command. And then I actually do it. So here's where I'm actually running that gzip command and capturing the return code. And then I test the return code to make sure it's 0. And if everything looks good, I go ahead and remove the file. I have one more step here where a little bit of sanity checking saying, let's make sure that compressed file actually does exist. So this is another utility function in OS that checks to see that a file exists. If that's not true, something went terribly, terribly wrong. And I want to stop, I want to throw on the emergency brake here. So I'm going to print that it failed, and I'm going to call this function here, which immediately stops the program from running. And itself returns a 1 exit status, which means something terrible happened. So this part up here that I skipped over, file name. So you just have to keep in mind, the file here is just the name of the file itself. It doesn't contain the whole directory tree above it. And I need that for my gzip command. I need the whole path to the file. So I'm going to construct it here by combining path and file and calling that file name. So this is giving me the true full name of the original file. And then I'm going to create a new file name by replacing fastq with fastq.gz. So just giving you some more examples of some kind of fun string functions. This is really dangerous, of course, right? Because I'm nowhere here in my testing that .fastq comes at the end of the file. So if for some strange reason I had that at the beginning of the file, the middle, this would do totally the wrong thing. So another example of why you have to program very defensively. So there's lots of things in this program that would cause me to not actually do this on real data, but it's a good example. Okay, so again, if we wanted to execute that, we would do it this way, and I can go ahead and do that. I'm going to clean things up from a previous run of that, and then I go ahead and say Python ex2.py and ex. So it takes one parameter, ex2dir, and you can see it discovered 2 fastq files, as we would expect, and compressed each one of them. If I actually take a look at the find is a nice Linux command, if you're not familiar with it, that sort of wanders through a directory tree and prints everything it finds, among other things. You can see that we compressed those files. So it actually worked. Any questions about that one? Okay. So the third example is a more complicated example. And it's an attempt to kind of show you a couple of things. How to build sophisticated data structures that can make your code more efficient, and how to make use of some really powerful libraries, a really powerful library that has some nice classes, and also using dictionaries. So I guess those 3 things. So here's the problem. Somebody gives you a file, genes.txt, that's what's in the trade is called a gene annotation file. So it's got a line for every gene that's in some genome, let's say the human genome. And this is a very simplified version of it, but it's got a gene name and which chromosome that gene's found on, and is it found on the plus strand or the minus strand, and within chromosome 1, what's its extent and its position within the chromosome. So it starts at location 11873 and goes to whatever. Real gene annotation files are a little more complicated than this, but it's sort of the same spirit, and they could be easily hundreds of thousands of lines long. So they can be very big files. So that's one kind of file. And another kind of file is the sort of file that you get out of a big DNA sequencer, one of these high throughput DNA sequencing machines. So I don't know if you're not familiar with how those work. They basically take a whole bunch of DNA and chop them into tiny little bits, and then analyze each of the tiny little bits and produce the string of characters that describes that little piece of DNA. And so bunches of A's, T's, C's, and G's. And the beauty of the modern world with high throughput sequencers is they're really efficient, and they can create hundreds of millions of these things very cheaply. So you end up with these enormous files full of these little snippets of characters that represent DNA. And typically what happens then is they'll use a sequence mapper to find the place in the reference genome where that particular sequence appears to match. And then you'll get a mapped sequence file. So that's what this is an effort to represent. So it's saying our machine found this snippet of DNA, and we think it occurs on chromosome 1, starting at this position, and we've given that particular snippet the name sequence 1. So they typically give an ID for each of the sequences. It's just a counter, just an index. So, and these files can be really big, hundreds of gigabytes, terabytes. So very large files. So what we'd like to do for this problem is figure out for each of our sequences in this very large file, which genes, if any, does it overlap with? Okay, so it's kind of by its nature, it's a little bit of an n squared problem. We've got n, a very large n of numbers of sequences, and a very large, let's say m, of not quite as large, but still pretty large number of genes. And if they overlap, if we said, well, we think this piece of DNA starts at this position, and given its length, it would end at that position, which of our genes does it overlap with? So we see people doing stuff like this. Is a very common thing to ask, and we see people doing this all the time. And the most common way that they'll implement this is they'll read all of the genes into memory, and they'll take one sequence, and they'll go through each gene one by one and say, does it overlap? And if it eventually does, they find one, then they'll print out something. And then they'll take the next one and do that. And that turns out to be really, really, really slow and pretty memory intensive. If you do that the wrong way, basically your code will never end. It'll just compute forever. So we find people doing that because we see these codes that seem to have been running for a very long time. So there's a better way to do that. And the key is this Python library called interval tree. So interval tree has nothing to do with DNA. It's a more abstract kind of mathematical idea. It understands intervals. So it understands start and end of a kind of an extent of something. Think of it as like a line on a number line. And it allows you to store intervals like that in a very efficient way, and then take another interval and compare it to what you have, and very, very quickly find anything that overlaps. And it's using an incredibly sophisticated data structure under the covers to do that without having to search through every interval to find the answer. Okay, I think it's using B trees, but in any case, it's using a very sophisticated storage algorithm so that it can very quickly zero in on candidate intervals. So that's what we're going to use. So I want to show you how that works. So interval tree is a library that doesn't come with Python by default, but you can install it, say by using conda, like I mentioned, which I've done in the version of Python I have here. This is actually an example of something that came up earlier, a question. Here, I've said from interval tree, import interval tree, so I can just directly call interval tree without having to say interval tree dot interval tree. which I think why I did it, because that seemed irritating. So, and they have a kind of cool syntax. They overloaded the slicing syntax. So this is kind of interesting, actually. So there's a more traditional function way to use interval tree, but they created this syntax, which is really natural. So this says, I want to create an interval that runs from 4 to 7, an interval that runs from 5 to 10, and an interval that runs from 1 to 11. So I'm creating 3 intervals in my interval tree. And I give them these names. So, so this little bit of code here has created an empty interval tree and installed into it 3 intervals. So I'll go ahead and run that. So here's an example again, like how do you print an interval tree? Well, the people who invented the interval tree, who implemented it, said this is how we'll print it. We'll describe each interval this way, and we'll print it as this interval tree. That was a choice when they implemented how to actually represent it as a string. So we've got this thing that has 3 intervals in it, and now we can query it. And this is what that looks like. You can just give any additional interval and say who overlaps with this. So actually, let me do something simpler first. Does anything, if I have another interval 1 to 3, who does that overlap with? Well, we look at it, looks like gene 3 overlaps with that, right? Because gene 3 goes from 1 to 11. So sure enough, gene 3 is the one that overlapped with that. If I do 1 to 5, I get 2 results back. I get the 4 to 7 and the 1 to 11. I don't get the 5 to 10. And here's another example of this kind of quirky thing where the interval from 1 to 5 doesn't quite go to 5. It goes just 2, but not including 5. So, so that's why you don't get this one. But if I did 6, I would get all 3. Okay, this is a sort of a detail, but the important point here, and of course it's not at all evident with an interval tree that only has 3 entries, is even if this interval tree held millions of entries, this lookup would still be really fast. And that's because of the way the interval tree under the covers is implemented. Okay, so what's our general plan? Basically what we want to do is make an interval tree and plug all the genes in there, and then take one at a time those DNA sequences and figure out the interval they describe. For each one, what interval does it describe? Well, it's where it begins and its length tells you where it ends. Compare it to our interval tree of genes, get all the matches out, all the overlaps, and print them. So it's all very straightforward. There's one little catch here, which is that the way the human genome is numbered, let's say this is human stuff, is it's chromosome by chromosome. So for each chromosome, you start again at 1. So position 5,000 on chromosome 1 is different from position 5,000 on chromosome 2 and chromosome 3. So in fact, once you think about it, we're going to actually need to have more than one interval tree. We're going to need to maintain an interval tree for each chromosome. So that's kind of the only trick. So we're going to end up with multiple interval trees, 1 per chromosome, and we're going to have to organize those somehow. So to me, the most natural way to organize them is a dictionary. So we're going to tag each interval tree by the name of its chromosome. So a sort of a schematic here, what we want to end up with as our data structure is one big dictionary that has a bunch of entries in it. Chromosome 1, chromosome 2, chromosome 3, those are the keys. And the values for each of those keys aren't integers like what we saw before in the simple dictionary. Instead, they're full-fledged interval trees. So chromosome 1 is associated with the interval tree that holds the data for chromosome 1, and so forth for all the other chromosomes. Okay? So that's going to build us this very interesting and sophisticated data structure that'll be exactly what we need when we go ahead to do the lookup. So what does a pseudocode look like for that? We create an empty dictionary. We open the gene annotation file. We read it line by line, parse it just like we've been doing before. We're going to parse it and get out the name of the gene, the chromosome. We'll throw away the strand because we're not interested in that for this particular case. And we'll get the start and end position. Then we're going to create an interval for that in our interval tree. We just have to be a little bit careful. If this is the first example of if this gene is the first example we've seen for some given chromosome, then we don't have an interval tree for that chromosome yet. We'll have to create an empty one. So that's sort of like a check we'll have to do. Once we've done that, we've got an interval tree for it, whether empty or not, and we'll just plug this interval in there. And then we'll repeat for the next one. So we're just going to keep doing that for every entry in the gene annotation file until we've done them all. So that the code actually looks like this. This stuff at the top should look pretty familiar. Here's where the fun starts. So we've opened the gene annotation file. We passed the name in as an argument, and line by line, we're going to process it. This is exactly the same kind of parsing we did before. In this case, before we did the split using a comma, in this case, this is a white space separated file, not a comma separated file. And that's what line split defaults to using white space as the separator. So we just leave this empty. So line split will give us the individual components. I should have actually said this before, I'm sorry. This is a really interesting assignment. It's a multi-value assignment. So line split actually produces 5 values turns out it does it as a list. So we've got 5 values on the right and 5 variable names on the left. It just does a bulk assignment. So that like looks so natural, you don't even ask about it, but it is a little weird. So so now we have our name, our chromosome, and our start and our end. That's what we care about. Down here, we're going to actually insert the new interval. I'm skipping these 2 lines here for a second. So this is a little complicated, but basically start and end are strings we got out of the file. We want to be careful here, actually. You could use the strings in your intervals, but then the wrong thing would happen because it would use string ordering instead of integer ordering. We want to use integer. We want 99 to be less than 100, right? If we used string ordering, 99 would be greater than 100 because 9 comes before 1. Right? It's just the way strings order is different from the way integers order. So we want to use integer ordering. So that's why we do have to do this conversion here. So that's all that's going on here. We're converting start and end to integers. But other than that, it's the same thing we saw before. We got this colon. And then rather than directly referencing the table, we're, the interval tree, we're finding the interval tree by pulling a particular value out of our table, out of our dictionary, which is keyed by the chromosome. That's what's happening up here. So we're saying, have we seen this chromosome before? This is kind of a nice shorthand too. You can say is value in dictionary, and that will return a true or false, whether or not that key exists in the dictionary. So if we have not yet seen an example of this chromosome yet, then there's no interval tree for it in the table yet, and we need to create one. So that's what happens here. We create a brand new empty interval tree and assign it into the dictionary that we call table. So I know that's kind of dense code, but are there any questions about any parts of that? And basically, we're running through the genes one by one, inserting the appropriate interval into the appropriate interval tree, and if we need to, generating the interval tree first. At the end of the day, that's what's happening. Okay. Oh, I've got a raised hand.
Ask, is in this particular application, how would you incorporate the strandedness to make sure that it's also like the same?
Yeah, so the question is, how would you include the strandedness? I haven't thought about that. I probably wouldn't, but it's not really my area of expertise. So I'm not sure. I mean, what would that say? I don't really think it's relevant to what we're doing here. If you assume all we're really caring about is the extent, the positional extent of either the read or the gene. And so which way you're reading, which direction you're reading in, I don't think really matters. You could, yeah, I don't think I have anything more intelligent to say about that, actually. Okay, so I'm going to go ahead and execute this code. And so this will actually take a perceptible amount of time because the genes.txt file that I'm using here is actually not a completely trivial file. I think it's 80,000 lines of, so it's got 80,000 gene annotations in it. So it'll take it a second or two to actually run on my poor little machine here. Okay, so it finished. So now what we have, table is a very large data structure. It's a dictionary containing, it's not 22, so right, how many chromosomes are in this data? I actually don't know exactly, but this data is a little messy. So it's got all the standard human chromosomes and then some kind of offbeat ones. And that's an advantage to the way I did this. I didn't make an a priori assumption. I know the names of the chromosomes in this data. I said, you know, when I find them, I'll put them in the table. So we could actually ask, let's see, can I don't want to print the table because it's really big. But I could do, actually, let's be in one more careful. I'm going to, the length, how many keys are there in this table? Okay, so there's 60, it found 60 separate chromosomes in this data. So like I say, there's the 22 plus, I think, mitochondrial X and Y, and then some kind of weird snippets. But like I say, we wouldn't want to print out, it would, if I said print table, it would dutifully print everything and it would scroll forever. But what we can do that's a little more interesting, we could do a sample query. So we could say, what is in the table on chromosome 1 between these positions? So it found 5 genes that overlapped with sort of between those 2 points. So that gives you a sense of how this works. Okay, so that's the kind of query that we're going to want to do. So, so that was step 1, to build the data structure. Step 2 is to open up our mapped reads file and process each one by doing a lookup. So we're open the file, read through the file, again parse it just like we've been doing, and then based on the chromosome that this particular read mapped to, get that interval tree and do the lookup. So here's what that code looks like. So this is something that you haven't seen before. Here, rather than writing the output to the screen, I'm going to write it to a file. So this is a very useful thing to know how to do. This again, it feels very C-ish to me. So it's the same open, but you notice there's this new argument here, this W. That means open it in write mode. So this is a write file pointer instead of a read file pointer. Previously, I could have put this here and said R. So I could have had quote R quote in my other opens before, but that's the default, so I didn't need to. So the default when you do an open is read. If you want to do something else, you need to specify. Here I'm saying I want to write to this file. So this is the same as before. So file, so arg3 is my output file. I'm going to have two parameters to this code. I'm actually going to have three. I'm going to have the genes file, the mapped reads file, and the output file when this is all put together. So this is reading from the mapped reads file. This is the same stuff we've been doing, parsing it. And then here is where I do the lookup. So again, I need to convert my pos, and it's a string right now because it came out of a string read on a file. I got to convert it to an integer. And I don't know if you remember this, but in that file, it didn't say begin and end. It just said begin. So I'm going to approximate the end by adding the length of the sequence. So my interval is going to be the position, from the position to the position plus the length of the sequence. It's not completely correct, but close enough. So that's my my sort of indices, and then I'm going to look that up based on pulling the appropriate interval tree out of the table using the chromosome. That will give me a list of intervals that I'm assigning to genes. And here, so this is an example of an if using something interesting as a test. So if my test here, if my query here came up empty, there were no overlaps, then genes is an empty list, and an empty list is a false. So if empty list will be false and I won't do anything. But if there are any overlaps, then it's a non-empty list, then this test is true, and I'll do this code here. So it's just basically going to print some information about the mapped sequence, and then for each of the genes I found, I'm going to print stuff about them as well. Okay, so I should be able to execute this. So for sanity's sake, my mapped reads file is very short. I think there are 3 elements in it, so we won't get a lot of output. Yeah, so there were 3 sequences in my input map file, and each of them found some overlaps, 2, 3, and 1. So, so that's how that works. So we're at the end of the time. There's a 4th example here, which I had no confidence I'd get to anyway, but you might find it fun to do. It's a much more complete example. It's doing the traveling salesman using simulated annealing. So if that sounds interesting, it's basically, if you don't know the traveling salesman problem, it's a really fun, surprisingly difficult problem to solve optimally. It's an optimization problem. And because to do it optimally is essentially impossible, there are a lot of heuristics for how to approximate good solutions to it. And this is kind of a fun one that I think you might find interesting. So feel free to look at that. And so the code kind of, I go sort of function by function here. So just two last slides to kind of finish up. Let's see, so the first slide is, I just want to tell you about some important packages that none of these I've talked about today, but they're sort of next steps for very useful Python packages. Numpy and SciPy are really important for doing sort of serious numerical processing. So rather than using lists, they have much more efficient data structures for holding matrices and doing operations on matrices, etc. So once you're doing stuff like that, you don't want to be using lists. Multiprocessing is a very easy way to write parallel Python programs. Matplotlib is, it turns out there are a shocking number of plotting packages in Python, but Matplotlib is kind of the standard one for generating plots. Pandas is incredibly cool. It's if you've used R and data frames, it's basically a rewrite of all of that. And if you haven't used those things, it's worth, if you do any statistics, data frames are kind of fascinating, especially when you get more complicated applications of them. And then there's some really nice frameworks for doing web stuff, like Flask. Flask is a sort of nice one, and Web2Py I like as well. So if you're building web applications, those are a couple of examples. And then just a few going further resources. I've forever have liked the O'Reilly Press, so I have some O'Reilly books here. The PyCharm debugger, it's really interesting. You can do so much with Python without ever using a debugger that I have not really done much with a debugger. Like you just don't seem to need it the way you do with C, but there are very good debuggers out there. And for people who like IDEs and debuggers, PyCharm is a good one. And then I've got at the bottom there some much more involved courses that will take you through much more deeply than what I did today. I think I'm ready for final questions.
Yeah, I have a question about the packages. Do we have to import all of them, or for example, does Numpy includes what SciPy and Panda got already?
SciPy, if I remember this correctly, SciPy includes, so there are dependencies, which is kind of how I would think about it. Pandas definitely requires NumPy. SciPy requires NumPy. I don't think SciPy and Pandas require one another. It's a little complicated, but basically NumPy is the basis for both of those other things, because it's really the library that makes multidimensional arrays efficient. I saw another hand, but I'm not hearing anything. Okay. Yeah, I'm sorry. The audio for me is really faint, so it's a little hard for me to hear sometimes. Well, why don't we end there? Thank you very much for your attention, and I apologize if the technical aspects of this weren't as smooth as I hoped, but we seem to have mostly gotten through it. So I appreciate your patience with it. Oh, okay.
I was just applauding to say thank you.
Okay, thanks. Nice.